Right now, you are traveling through space at over 500,000 miles per hour. You cannot feel it. You cannot see it happening. But you and everyone you know are passengers on a planet orbiting a star that is racing around something so massive, so impossibly large, that light itself takes 100,000 years to cross from one edge to the other. This is the Milky Way, our home. And compared to what exists beyond it, we are smaller than you can possibly imagine. We will journey from the tiniest galaxies containing just 1,000 stars to structures spanning nearly 100 billion light-years. We will measure the Milky Way against giants 40 times its size and discover our exact position in a universe filled with 2 trillion galaxies. If you enjoy this journey through cosmic scales, consider subscribing. Prepare yourselves. We begin. Look up at the night sky. That glowing band of light stretching across the darkness is not a cloud. It is not mist. It is the combined light of billions of stars so distant that they blur into a river of luminescence. You are seeing your own galaxy from the inside, and here is the problem. We cannot step outside to see what we truly live within. Imagine living your entire life inside a forest. Every tree you see is part of this forest, but you have never climbed high enough to see where the forest ends or what shape it takes from above. That is our situation with the Milky Way. We are trapped inside it, 27,000 light-years from its center, trying to map an object that surrounds us completely. For thousands of years, humans had no idea what that band of light actually was. Ancient Greeks called it Galaxias Kyklos, the Milky Circle. They thought it might be milk spilled by a goddess. Romans told stories of a celestial road. Chinese astronomers called it the Silver River. None of them knew they were seeing their own cosmic home from the inside. It was not until 1610 that Galileo Galilei pointed his primitive telescope at that glowing band and discovered the truth. What looked like continuous light was actually composed of countless individual stars packed so densely together that the human eye could not separate them. Each pinpoint of light was a blazing sphere, like our own star, just incredibly far away. But even Galileo could not grasp the full picture. He saw stars, yes, but he did not know they were arranged in a massive spinning disk. He did not know that this disk stretched so far that light, traveling at 671 million miles per hour, would need 100,000 years to cross from one side to the other. We now know the Milky Way is a spiral galaxy. It has a bright central bulge packed with older yellow and red stars. Extending from that bulge are several spiral arms, great curved structures where new stars are constantly being born in clouds of gas and dust. These arms wrap around the center like water swirling down a drain, except this drain is 100,000 light-years wide. Our entire solar system sits on the inner edge of one of these arms, called the Orion Arm. From our position, when we look toward the center of the galaxy, we see that dense band of light. When we look away from the center, toward the outer edge, we see fewer stars and more darkness. This is why the Milky Way appears as a band rather than surrounding us uniformly. We are not at the center. We are off to one side, getting a sideways view through the disk. The galaxy is also incredibly thin compared to its width. If you scaled the Milky Way down to the size of a dinner plate, it would be thinner than a sheet of paper. This flatness is why we see it as a band across the sky rather than a sphere of light surrounding us. And here is what makes our situation even more challenging. Dust. The Milky Way contains enormous clouds of dust particles that block visible light. When we look toward the galactic center, we cannot see all the way through. Billions of stars are hidden from our view, obscured by these cosmic clouds. Astronomers call this the zone of avoidance, a region of the galaxy we simply cannot observe with ordinary telescopes. To map our galaxy, scientists have had to use radio waves, infrared light, and careful measurements of star positions and movements. They have had to piece together a picture of the Milky Way by observing it from the inside, one section at a time, like trying to draw a map of your house while locked in a closet. What they have discovered is both humbling and extraordinary. But understanding the Milky Way is just the beginning, because when you zoom out, when you pull back to see where the Milky Way sits in relation to everything else, the scale becomes almost incomprehensible. The Milky Way contains between 200 billion and 400 billion stars. Stop and consider that number for a moment. 400 billion. If you tried to count them, one per second, without sleeping or stopping, it would take you over 12,000 years to finish. Each of those stars is a massive sphere of burning hydrogen, most of them larger than our own. Many have their own planets. Some have multiple planets. Current estimates suggest there are at least 100 billion planets in the Milky Way, and possibly as many as the number of stars themselves. Billions of those planets are roughly the size of Earth. Billions more orbit in the habitable zone where liquid water could exist. You live on one of those planets. One world among 100 billion or more. Your entire civilization. Every human who has ever lived, every story ever told, every war ever fought, has taken place on this single rocky sphere, 8,000 miles across. Now consider this. Our star is located about 27,000 light-years from the center of the galaxy. That means light from the galactic center, traveling at its incredible speed, takes 27,000 years to reach us. If an astronomer living near the galactic center looked at Earth right now, with a powerful enough telescope, they would see Earth as it was 27,000 years ago, during the Stone Age. We orbit the galactic center, just like Earth orbits our star, but this orbit is vastly larger and slower. Our star, dragging the entire solar system with it, moves at approximately 514,000 miles per hour through space. At this speed, it takes roughly 230 million years to complete one full orbit around the galaxy. Think about that timescale. The last time our star was in its current position relative to the galactic center, dinosaurs had not yet appeared on Earth. The next time we return to this spot, 230 million years from now, every continent will have shifted to new locations. Species we cannot imagine will likely have evolved and gone extinct. Despite moving at over 500,000 miles per hour, we feel nothing. The motion is too smooth, too constant. Just as you cannot feel Earth rotating on its axis or orbiting around the central star, you cannot feel the Milky Way carrying you through the cosmos at speeds that would cross the entire United States in less than 6 seconds. From our position out in the Orion Arm, we are relatively isolated. The nearest star to us, Proxima Centauri, is over 4 light-years away. That is roughly 25 trillion miles. If you tried to drive there at highway speeds, the journey would take more than 40 million years. Even traveling at the speed of a spacecraft, it would take tens of thousands of years with current technology. Yet despite these vast distances between stars, the Milky Way is far from empty. Between the stars lies gas and dust, the raw materials for future star formation. There are also objects we cannot see with ordinary light, black holes, neutron stars, and vast clouds of dark matter holding the galaxy together through gravity alone. If you could somehow view the Milky Way from outside, from a distance of several million light-years away, it would appear as a beautiful spiral structure glowing against the darkness of space. You would see the bright central bulge, the sweeping spiral arms traced by brilliant blue stars, and the faint outer halo where ancient stars drift in elongated orbits. But you would not be able to pick out our star. Among 400 billion points of light, it would be utterly invisible, too faint and ordinary to distinguish from countless others. Our entire solar system, with all its planets and moons, would occupy less than a single pixel, even in the most powerful telescope imaginable. This is the scale of the Milky Way, vast enough to contain hundreds of billions of stars, yet still just one galaxy among many. And the distances we have discussed so far, the thousands of light-years separating us from the galactic center, are nothing compared to what comes next. Because the Milky Way, as enormous as it is, does not exist alone. 514,000 miles per hour. That is how fast you are moving right now through the Milky Way galaxy. To put that in perspective, a bullet fired from a rifle travels at roughly 2,000 miles per hour. You are moving 257 times faster than a speeding bullet, and you cannot feel a thing. This motion is not the same as Earth's rotation or its orbit around the central star. Those motions are small compared to the vast carousel of the galaxy itself. Right now, our entire solar system is being carried along one of the Milky Way's spiral arms, sweeping around the galactic center in a circle so enormous that it defies human intuition. At 514,000 miles per hour, you would cross the distance from Los Angeles to New York in less than 7 seconds. You would circle Earth's equator in under 3 minutes. Yet, at this incredible speed, it still takes 230 million years to complete one orbit around the galaxy. This tells you something profound about the scale we are dealing with. The Milky Way is so vast that even moving at 500,000 miles per hour feels like standing still. The stars around us appear fixed in the sky, unchanging over human lifetimes, because the distances are simply too great for motion to be perceptible. But the galaxy is not just carrying us in a circle. The Milky Way itself is moving. The entire galaxy, all 400 billion stars together, is traveling through space at approximately 1,300,000 miles per hour relative to the cosmic microwave background radiation left over from the Big Bang. Where is it going? Towards something called the Great Attractor, a massive concentration of galaxies that exerts gravitational pull on everything in our region of the universe. We are being pulled, along with thousands of other galaxies, toward this distant gravitational center. And there is more. The Milky Way and the Andromeda Galaxy are moving toward each other. Despite being separated by 2.5 million light-years, they are approaching at roughly 250,000 miles per hour. In approximately 4 billion years, they will collide and merge, creating a new, larger galaxy that astronomers have already nicknamed Milky Way. When that collision happens, the speeds involved will be staggering. Two galaxies, each containing hundreds of billions of stars, will pass through each other at speeds measured in hundreds of thousands of miles per hour. Yet because stars are so far apart relative to their sizes, actual collisions between individual stars will be extremely rare. The galaxies will merge not through violent impacts, but through the slow, gravitational dance of matter responding to matter. So, at this very moment, you are participating in multiple motions simultaneously. Earth spins on its axis at about 1,000 miles per hour at the equator. Earth orbits our star at roughly 67,000 miles per hour. Our star orbits the galactic center at 514,000 miles per hour. The Milky Way moves through space at over 1 million miles per hour. And all of this is happening while the universe itself expands, carrying distant galaxies away from us at speeds that increase with distance. Add up all these motions, and you get a dizzying picture of reality. Nothing in the universe is standing still. Everything is moving, often in multiple directions at once, at speeds that would seem impossible if we could actually feel them. The reason we perceive none of this motion is simple. We are moving with everything around us. Just as you do not feel the motion of an airplane when it is cruising smoothly at altitude, you do not feel the galaxy carrying you through space. There is no wind, no sense of acceleration, nothing to push against. You are simply following the same path as everything else in your local environment. But the motion is real, and it is relentless. Every second, you travel thousands of miles through space. Every hour, you cross distances that would take months to travel with the fastest spacecraft ever built. Every year, you complete a journey of billions of miles around the galactic center, never arriving, never stopping, forever caught in the galaxy's gravitational grip. This motion has been happening for billions of years. Our star has completed roughly 20 orbits around the galaxy since it formed 4.5 billion years ago. Each orbit exposes us to different regions of the galaxy, different concentrations of gas and dust, different clusters of nearby stars. And this perpetual motion will continue for billions of years more until the galaxy itself changes beyond recognition. How do you measure something when you are trapped inside it? This was the challenge facing astronomers for centuries. From our position within the Milky Way, determining its true size seemed impossible. No human could step outside to take measurements. No spacecraft could travel far enough to see the galaxy from the outside. Yet somehow, through clever observation and mathematical reasoning, scientists figured it out. The story of how they did this is as remarkable as the discovery itself. The first breakthrough came from understanding what a light year actually measures. Light travels at 671 million miles per hour. In 1 year, it covers roughly 5.88 trillion miles. This distance, called a light year, became the standard unit for measuring cosmic distances, because everything in space is simply too far away to measure in miles or kilometers. But knowing the unit is not enough. You need a way to determine actual distances to stars. For nearby stars, astronomers use a technique called parallax. Hold your finger up at arm's length and look at it with just your left eye. Now look at it with just your right eye. Notice how your finger appears to shift position against the background. That shift is parallax. Earth orbits our star, so our planet's position changes by about 186 million miles every 6 months. By observing a nearby star in January, then observing the same star in July, astronomers can measure how much the star appears to shift against more distant background stars. The amount of shift reveals the star's distance through simple geometry. This method works beautifully for stars within a few hundred light years. But for more distant stars, the parallax becomes too small to measure accurately, even with the most sophisticated telescopes. So astronomers needed other methods. One powerful technique uses what are called Cepheid variable stars. These are stars that regularly brighten and dim in a predictable pattern. In 1912, astronomer Henrietta Leavitt discovered that the period of this brightening and dimming is directly related to the star's true brightness. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. This discovery was revolutionary. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate its distance. It is like seeing a light bulb in the distance. If you know it is a 100-watt bulb, you can estimate how far away it is based on how dim it looks. Using Cepheid variables, astronomers began mapping the three-dimensional structure of the Milky Way. They discovered that our galaxy is not a random collection of stars, but an organized disk with spiral arms. They found that certain types of stars cluster in the central bulge, while others are found primarily in the outer disk. Radio astronomy provided another crucial tool. Hydrogen gas, the most abundant element in the universe, emits radio waves at a specific frequency. By mapping these radio emissions, astronomers could trace the spiral arms of the galaxy even through the dust clouds that block visible light. This revealed structures we could never see with optical telescopes. More recently, the Gaia Space Telescope has been measuring the precise positions and motions of over 1 billion stars in the Milky Way. By tracking how stars move over time, astronomers can work backward to determine their distances and map the galaxy's structure in unprecedented detail. Through these combined methods, we now know the Milky Way has a diameter of approximately 100,000 light-years. The central bulge is about 10,000 light-years thick. Our position is about 27,000 light-years from the center, placing us roughly 40% of the way out from the center to the edge. We also know the galaxy contains 4 major spiral arms and several smaller arm segments. Stars in the inner galaxy orbit faster than those in the outer regions, causing the spiral pattern to wind up over time. New stars form primarily in the spiral arms, where gas and dust are compressed by the density waves moving through the disk. But even with all this knowledge, mysteries remain. We cannot see through the dust to observe the very center of the galaxy directly in visible light. We must rely on radio, infrared, and X-ray observations to peer into that hidden core. And we still do not know exactly how many spiral arms the Milky Way has, because observing the overall structure from inside remains fundamentally difficult. Measuring the Milky Way from within is like trying to draw a map of a city while walking its streets. You can measure individual blocks and neighborhoods, but assembling those measurements into a complete picture requires careful work and occasional educated guesses. Yet despite these challenges, we have succeeded. We know the scale of our galaxy, we know our place within it, and that knowledge makes the next revelation even more startling. Because measuring what lies beyond the Milky Way revealed structures even more immense. At the very heart of the Milky Way, hidden behind thick clouds of dust and gas, lurks something so massive and so powerful that its gravity dominates the entire galaxy. It is called Sagittarius A star, and it is a supermassive black hole with a mass 4.1 million times greater than our central star. Black holes are regions where gravity has become so intense that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives, compressing matter into an infinitely dense point called a singularity. Around this singularity, there exists a boundary called the event horizon. Cross that boundary, and you are gone forever, pulled inexorably toward the center with no possibility of return. But Sagittarius A star is not a stellar black hole formed from a single collapsed star. It is a supermassive black hole, millions of times more massive, and scientists are still not entirely certain how such monsters form. They may grow slowly over billions of years by consuming gas, dust, and stars, or they may have formed very early in the universe's history through processes we do not yet understand fully. This black hole sits approximately 27,000 light-years from Earth, at the exact center of the galaxy. Despite its enormous mass, the black hole itself is not large in the way we typically think of size. The event horizon, the point of no return, has a diameter of about 14 million miles. That sounds massive, but it is actually smaller than the orbit of Mercury around our star. What makes Sagittarius A star so influential is not its size, but its gravity. All the stars in the inner galaxy orbit around this central mass. Astronomers discovered its existence by carefully tracking the motions of stars near the galactic center. These stars move at extraordinary speeds, some reaching several million miles per hour, as they whip around the black hole in elliptical orbits. One star, designated S2, completes an orbit around Sagittarius A star every 16 years. At its closest approach, this star comes within just 11 billion miles of the black hole, traveling at roughly 5,000 miles per second. That is nearly 2% the speed of light. By observing the motion of S2 and other nearby stars, astronomers calculated the mass of the black hole with remarkable precision. For most of its existence, Sagittarius A star is relatively quiet. It is not currently consuming large amounts of matter, so it does not produce the brilliant jets and enormous radiation output seen in some other supermassive black holes. Occasionally, though, something strays too close. A cloud of gas, or perhaps an unlucky star, wanders into the black hole's gravitational grip. When this happens, the material does not fall straight in. Instead, it begins orbiting the black hole, forming what is called an accretion disk. Friction in this disk heats the material to millions of degrees, causing it to emit X-rays and gamma rays. These brief flares tell us that the black hole is feeding, pulling matter across the event horizon and adding to its already stupendous mass. Scientists have also detected strange objects near the galactic center called G-clouds. These are dusty, gaseous structures that orbit close to Sagittarius A star. Some astronomers think these might actually be stars hidden within cocoons of gas and dust. Others believe they could be the remnants of stars that have been partially torn apart by the black hole's tidal forces. The region around Sagittarius A star is one of the most extreme environments in the galaxy. Radiation levels are intense. Stars are packed so densely that collisions between them might occasionally occur. Gravitational forces can stretch objects into long, thin strands through a process called spaghettification. Any planet unfortunate enough to orbit near the galactic center would be bombarded by radiation and subjected to gravitational forces that would make stable orbits difficult or impossible. Yet despite its power, Sagittarius A star does not threaten us. We are 27,000 light-years away, far enough that the black hole's gravity is no stronger than the gravity from an equivalent mass of ordinary matter. The galaxy does not spiral into the black hole because the stars are in stable orbits, held in balance between gravity and their motion through space. In 2018, astronomers achieved something remarkable. They captured an image of the event horizon of a supermassive black hole, not Sagittarius A star, but a similar black hole in the center of the galaxy, M87. 55 million light-years away. The image showed exactly what theory predicted: a dark circle surrounded by glowing material, the shadow of the event horizon itself against the bright accretion disk behind it. Work is underway to produce a similar image of Sagittarius A star. When that image arrives, we will see the heart of our own galaxy for the first time, the supermassive secret that has shaped the Milky Way for billions of years. But while our galaxy has one central black hole, other cosmic structures dwarf even this impressive monster. The Milky Way does not travel alone through space. Circling around our galaxy like moths around a flame are more than 20 small companion galaxies, trapped in our gravitational grip. These are dwarf galaxies, cosmic structures so faint and diffuse that most of them were discovered only in recent decades. The largest and most famous of these companions are the Large and Small Magellanic Clouds. Visible from the southern hemisphere, they appear as fuzzy patches of light in the night sky. For centuries, they were assumed to be clouds or nebulae within the Milky Way. Only in the 20th century did astronomers realize they are separate galaxies in their own right. The Large Magellanic Cloud contains roughly 30 billion stars spread across approximately 14,000 light-years. That might sound substantial, but it is only about 10% the diameter of the Milky Way and contains less than 3% of our galaxy's stellar population. Yet, among dwarf galaxies, it is considered large. The Small Magellanic Cloud is even smaller, containing around 3 billion stars in a region about 7,000 light-years across. Both clouds orbit the Milky Way at distances of roughly 160,000 to 200,000 light-years. They are close enough that gravitational interactions with our galaxy distort their shapes and strip away streams of gas and stars. Astronomers have detected these stellar streams arcing through space, connecting the Magellanic Clouds to the Milky Way. This is evidence that our galaxy is slowly consuming its smaller companions, pulling them apart over hundreds of millions of years through tidal forces. But the Magellanic Clouds are giants compared to some of the other dwarf galaxies orbiting us. Most Milky Way satellites are so faint that they can barely be detected even with powerful telescopes. They are called ultra-faint dwarf galaxies, and they challenge our understanding of what constitutes a galaxy at all. Consider Segway 2, a dwarf galaxy discovered in 2009. It contains only about 1,000 stars. 1,000. That is fewer stars than many globular clusters, which are dense collections of stars within galaxies. Segway 2 is held together not by the gravity of its stars, which is far too weak, but by a massive halo of dark matter surrounding it. This invisible matter provides the gravitational glue that prevents the galaxy from dispersing. Another remarkable example is Andromeda XXXV, a dwarf galaxy orbiting the Andromeda Galaxy rather than our own. It is about 1/1,000,000th the mass of the Milky Way, and so dim that it was discovered only recently, despite being relatively nearby in cosmic terms. It is roughly as faint as a single candle viewed from thousands of miles away. These ultra-faint dwarfs raise a fascinating question. How did they survive? In the early universe, conditions were hotter and more violent. High-energy radiation from the first stars should have heated and dispersed the gas in small galaxies, preventing them from forming new stars. Many astronomers expected that galaxies this small would have been completely destroyed. Yet here they are, ancient and unchanged, with star populations that are billions of years old. They stopped forming new stars long ago, shortly after the Big Bang, and have simply coasted through space ever since. They are stellar ghost towns, fossils from the early universe. The Milky Way likely has many more dwarf satellites that have not yet been discovered. Some are hidden behind the dense star fields of our galaxy, making them nearly impossible to spot. Others might be so faint that current telescopes cannot detect them. Astronomers estimate there could be hundreds of these tiny galaxies scattered around the Milky Way, each containing anywhere from a few hundred to a few million stars. Some dwarf galaxies are not spherical, but instead stretched into elongated streams. These are the remnants of galaxies that have been completely torn apart by the Milky Way's gravity. The stars that once formed a coherent structure now spread along an orbit, creating a river of stars flowing around our galaxy. One example is the Sagittarius dwarf elliptical galaxy, which is currently in the process of being absorbed. It has already passed through the Milky Way's disk multiple times, and each passage strips away more of its stars. Eventually, nothing will remain but individual stars scattered throughout our galaxy, indistinguishable from stars that formed here originally. This is the fate of all dwarf galaxies that venture too close to the Milky Way. Our galaxy grows by consuming its smaller neighbors, adding their stars to its own population. Over billions of years, the Milky Way has likely absorbed dozens of dwarf galaxies, erasing them from existence and incorporating their matter into its own structure. But while the Milky Way dominates its dwarf companions, it is not the dominant galaxy in our local neighborhood. That distinction belongs to something much, much larger. 2.5 million light-years away, separated from us by an ocean of empty space, lies the Andromeda Galaxy. It is the nearest major galaxy to the Milky Way, and it is coming closer. Andromeda is larger than the Milky Way in almost every measurable way. Its disk stretches roughly 220,000 light-years across, more than twice the diameter of our galaxy. It contains approximately 1 trillion stars, 2 to 3 times more than the Milky Way's population. Its total mass, including dark matter, is estimated at around 1.5 trillion times the mass of our central star. If you could see Andromeda's full extent from Earth, it would appear 6 times wider than the full moon in the sky. We cannot see this with our eyes because most of the galaxy is too faint. Only the bright central core is visible as a fuzzy patch of light. But long exposure photographs reveal the galaxy's true majesty, a grand spiral with well-defined arms, glowing with the light of 1 trillion distant stars. Andromeda's sheer size is humbling. The Milky Way, which seems so vast when we consider our position within it, is actually the smaller partner in this cosmic duo. If the two galaxies were people standing side by side, the Milky Way would reach roughly to Andromeda's shoulder. Despite the enormous distance separating them, the two galaxies are gravitationally bound. They orbit around a common center of mass, and that motion is bringing them together. Spectroscopic measurements show that Andromeda is approaching us at roughly 250,000 miles per hour. This might sound fast, but given the distance involved, the two galaxies will not collide for approximately 4 billion years. When the collision begins, it will be a slow-motion catastrophe spanning hundreds of millions of years. The galaxies will initially pass through each other, their stars rarely colliding because of the vast distances between them. But the gravitational interaction will distort both galaxies, flinging stars into long tidal tails and triggering enormous bursts of new star formation as gas clouds collide and compress. After the first pass, gravity will pull the galaxies back together for a second collision, then a third. Each encounter will further scramble their structures. Eventually, over the course of roughly 1 billion years, the two galaxies will merge completely, forming a single large elliptical galaxy. The organized spiral structures will be destroyed, replaced by a more chaotic distribution of stars. Our central star will likely survive this merger. The chances of an actual collision between our star and another are extraordinarily small, but the gravitational chaos will probably eject our solar system from its current orbit, sending it either into the outer reaches of the merged galaxy or possibly out into intergalactic space entirely. If any civilizations exist at that time, they will witness a spectacular show as two galactic cores merge into one. Andromeda has its own population of dwarf satellite galaxies, at least 14 that we have identified so far. Some of these, like M32 and M110, are visible in telescopes and have been known for centuries. Others are ultra-faint dwarfs, similar to those orbiting the Milky Way, discovered only through careful analysis of astronomical surveys. Interestingly, Andromeda appears to have experienced major galactic collisions in its past. Astronomers have detected strange distributions of stars in its outer regions, suggesting it has already consumed several smaller galaxies. The scars of these ancient mergers are still visible in the streams and shells of stars that surround Andromeda's main body. At the center of Andromeda sits a supermassive black hole even larger than our own. Estimates place its mass at roughly 140 million to 230 million times the mass of our star, making it dozens of times more massive than Sagittarius A star. When the Milky Way and Andromeda merge, these two supermassive black holes will eventually spiral together and merge as well, releasing a burst of gravitational waves that will ripple through space-time itself. For now, though, Andromeda remains a distant neighbor, beautiful and imposing but far enough away that we can observe it in safety. On a clear night, away from city lights, you can see Andromeda's core with your naked eyes. The photons hitting your retina began their journey 2.5 million years ago, when early human ancestors were just beginning to use stone tools. Those photons traveled through intergalactic space for millions of years, passing through regions where matter is so sparse that a single atom might occupy several cubic feet of space. They passed by or through countless other galaxies on their journey, before finally arriving at Earth and entering your eye. Andromeda is the farthest object visible to the unaided human eye, the most distant thing you can see without technological assistance. It represents the edge of what our biology allows us to perceive. Everything farther requires telescopes, and when you point those telescopes outward, you discover that the Milky Way and Andromeda are not alone. They are part of something larger. The Milky Way and Andromeda do not drift through the universe in isolation. They are the two largest members of what astronomers call the Local Group, a collection of more than 50 galaxies bound together by gravity and spanning roughly 10 million light-years. This is our cosmic neighborhood, the closest collection of galaxies to our own. Understanding the Local Group is like understanding your local city or town. It provides context for where you live and how your home fits into the larger world. The Local Group is dominated by 3 spiral galaxies: the Milky Way, Andromeda, and the Triangulum galaxy. Triangulum, also called M33, is the third largest member, containing roughly 40 billion stars and stretching about 60,000 light-years across. It lies approximately 3 million light-years from Earth, making it slightly farther than Andromeda, but still very much a nearby neighbor. Everything else in the Local Group is smaller. There are dozens of dwarf galaxies, ranging from relatively substantial ones like the Large Magellanic Cloud down to ultra-faint dwarfs containing only thousands of stars. Most of these dwarfs orbit either the Milky Way or Andromeda, trapped by the gravity of their larger companions. The total mass of the local group is estimated at roughly 2 trillion times the mass of our star. But the vast majority of that mass is not in stars, gas, or dust. It is dark matter, the mysterious invisible substance that provides the gravitational scaffolding holding the group together. For every kilogram of ordinary matter in the local group, there are roughly 5 kilograms of dark matter we cannot see or detect directly. The local group occupies a relatively quiet region of the universe. It sits at the edge of a larger structure called the Virgo supercluster, far from the dense clusters of galaxies that dominate that supercluster's core. This isolation is fortunate for us. Galaxies in dense cluster cores experience frequent interactions and collisions, making stable environments for life more difficult to maintain. But even in our relatively calm neighborhood, interactions occur. The Milky Way and Andromeda are slowly approaching each other. As we have discussed, Triangulum may also be gravitationally bound to Andromeda, and some astronomers think it might eventually collide with Andromeda before the Milky Way does. These interactions will fundamentally reshape the local group over the next several billion years. Between the galaxies in the local group lies mostly empty space. The density of matter in intergalactic space is extraordinarily low, roughly 1 atom per cubic meter. For comparison, the air you are breathing contains approximately 10 trillion molecules per cubic meter. Intergalactic space is emptier than the best vacuum we can create in laboratories on Earth. This emptiness means that traveling between galaxies would require crossing vast expanses of virtual nothingness. If you could travel at the speed of light, it would take 2.5 million years to reach Andromeda from the Milky Way. At the speed of current spacecraft, the journey would take roughly 30 billion years, far longer than the current age of the universe. Despite these distances, the local group is actually quite compact compared to the larger structures in the universe. The entire group could fit inside a sphere about 10 million light-years across. That sounds enormous, and it is, but it is tiny compared to galaxy clusters and superclusters. Observing other members of the local group provides crucial information about galaxy formation and evolution. Because they are so close, astronomers can study individual stars in nearby dwarf galaxies, determining their ages, compositions, and motions. This allows us to reconstruct the history of these galaxies, figuring out when their stars formed and how they have changed over billions of years. Some local group dwarfs are ancient, with star populations dating back more than 10 billion years. Others show signs of recent star formation, suggesting they still have gas and are actively creating new stars. By comparing these different galaxies, astronomers can test theories about how galaxies form, evolve, and interact with their environments. The local group also provides a laboratory for studying dark matter. Because we can measure the motions of stars and gas in nearby galaxies very precisely, we can map the distribution of dark matter holding those galaxies together. This has revealed that dark matter forms extended halos around galaxies, reaching far beyond the visible stars. But the local group is not the only collection of galaxies in our region of space. It is actually a relatively minor component of a much larger structure, one so vast that it dwarfs everything we have discussed so far. This structure pulls on the local group, influencing our motion through space and determining our ultimate fate. The Milky Way is ordinary. This might come as a surprise after learning about its 400 billion stars, its supermassive black hole, and its 100,000 light-year diameter. But in the grand scheme of galaxies, the Milky Way is remarkably average. It is neither among the largest nor the smallest. It is not particularly bright or particularly dim. It is simply one typical spiral galaxy among hundreds of billions. This ordinariness is actually important. If the Milky Way were unusual, we might wonder whether our existence is connected to whatever makes it special. But because our galaxy is average, it suggests that galaxies like ours are common, and therefore places where life might develop are likely scattered throughout the universe. Galaxies come in several basic types, classified by their shapes. Spiral galaxies like the Milky Way have flat rotating disks with curved arms and a central bulge. Elliptical galaxies are three-dimensional, ranging from nearly spherical to highly elongated. Irregular galaxies lack organized structure, appearing as chaotic collections of stars. There are also lenticular galaxies, which have a disk and bulge like spirals but lack prominent spiral arms. The Milky Way is a barred spiral galaxy. This means it has a bar-shaped structure of stars running through its central region, with spiral arms extending from the ends of the bar. Roughly 2/3 of spiral galaxies have bars, so this feature is quite common. Our bar is about 27,000 light-years long, and it rotates as a rigid structure, completing one rotation every few 100 million years. The Milky Way's size places it in the upper range of typical galaxies. Most galaxies in the universe are actually much smaller. Dwarf galaxies vastly outnumber large ones. If you selected a galaxy at random from the universe, it would probably be a dwarf with fewer than 10 billion stars. In that context, the Milky Way's hundreds of billions of stars make it larger than average, but not exceptionally so. In terms of mass, the Milky Way is also fairly typical for a large spiral. Estimates place its total mass, including dark matter, at roughly 1 trillion times the mass of our central star. This is substantial, but there are many galaxies with similar masses. The Milky Way is not a heavyweight in the cosmic arena, nor is it lightweight. Star formation in the Milky Way proceeds at a moderate pace. Our galaxy produces roughly 3 new stars per year on average. Some galaxies, called starburst galaxies, form stars hundreds or even thousands of times faster. These galaxies burn through their gas supplies quickly, creating brilliant displays of young, hot stars. The Milky Way's more sedate rate of star formation suggests it will continue producing new stars for billions of years to come. The metallicity of the Milky Way, meaning the abundance of elements heavier than hydrogen and helium, is also typical. Older stars in the galaxy have lower metallicity because they formed when the universe was younger and contained fewer heavy elements. Younger stars have higher metallicity because they formed from gas enriched by previous generations of stars that exploded as supernovae, scattering heavy elements into space. One way the Milky Way might be somewhat unusual is in its relatively quiet central black hole. Some galaxies have supermassive black holes that are actively consuming large amounts of matter, creating brilliant quasars or active galactic nuclei that can outshine the entire rest of the galaxy. Sagittarius A star is comparatively calm, consuming matter at a trickle rather than a flood. This might be fortunate for life in the galaxy, as active galactic nuclei flood their surroundings with radiation that could sterilize nearby star systems. The Milky Way's location in a relatively sparse region of the universe might also be somewhat fortunate. Galaxies in the dense cores of galaxy clusters experience more frequent interactions and mergers, which can disrupt star systems and trigger bursts of star formation. The Milky Way's more isolated position has allowed it to evolve more smoothly, maintaining its spiral structure for billions of years. But these minor peculiarities do not make the Milky Way special. There are millions of other galaxies with similar properties scattered throughout the observable universe. Our galaxy is one example of a very common type of cosmic structure. This realization has profound implications. If the Milky Way is typical, and if life arose here, then life might also arise in countless other typical galaxies throughout the universe. The ordinariness of our cosmic home suggests that we might not be alone, that somewhere among those millions of similar galaxies, other civilizations might have developed. Of course, we do not yet know how common life is. We have no confirmed examples of life beyond Earth. But the fact that Earth orbits an average star in an average location within an average galaxy suggests there is nothing cosmically unique about our situation. What happened here could happen elsewhere. Yet even an average galaxy, like the Milky Way, is profoundly influenced by its environment. We do not float alone through empty space. We are part of larger structures, and those structures shape our motion and evolution. The nearest of these larger structures is already pulling us toward it. 60 million light-years from Earth, in the direction of the constellation Virgo, lies the densest concentration of galaxies in our region of the universe. It is called the Virgo cluster, and it contains more than 1,000 large galaxies, plus thousands of smaller dwarf galaxies packed into a region roughly 15 million light-years across. The Virgo cluster is a violent place by cosmic standards. Galaxies there move at speeds exceeding 1 million miles per hour, their motions dominated by the cluster's immense gravitational field. When galaxies collide in such environments, they can merge, ripping each other apart and triggering intense bursts of star formation. The space between galaxies is filled with hot gas at temperatures of millions of degrees, glowing in X-rays but invisible to the human eye. At the center of the Virgo cluster sits one of the largest galaxies known, M87. This giant elliptical galaxy contains several trillion stars and has a supermassive black hole at its core, with a mass of roughly 6.5 billion times that of our central star. That black hole is actively feeding, consuming matter and blasting 2 jets of plasma thousands of light years into space at nearly the speed of light. The Milky Way is not part of the Virgo cluster. We are too far away, but we are not immune to its influence. The Virgo cluster's enormous mass, roughly 1,000 trillion times the mass of our star, exerts gravitational pull on everything in the surrounding region of space. This includes the local group, which is falling toward the Virgo cluster at approximately 250 miles per second. This motion is on top of all the other motions we discussed earlier. We orbit the galactic center, the Milky Way moves toward Andromeda, and the entire local group falls toward the Virgo cluster. These motions combine into a complex trajectory through space, like a leaf caught in multiple currents of a river. However, recent discoveries have revealed that the Virgo cluster is not the ultimate destination. The cluster itself is moving, pulled by even larger structures beyond. The Virgo cluster, along with a local group and dozens of other galaxy clusters and groups, is part of a structure called the Virgo supercluster. A supercluster is a collection of galaxy clusters and groups spread across hundreds of millions of light years. The Virgo supercluster contains at least 100 galaxy groups and clusters, with a total estimated mass of roughly 100,000 trillion times the mass of our star. It is one of millions of superclusters scattered throughout the observable universe. For decades, astronomers believed the Virgo supercluster was the largest structure containing the Milky Way. But in 2014, a team of researchers led by R. Brent Tully published a revolutionary new map of our cosmic neighborhood. Using measurements of galaxy velocities, they defined superclusters, not by simple proximity, but by gravitational flow. Galaxies that move together, falling toward a common center of mass, belong to the same supercluster. This new definition revealed something stunning. The Virgo supercluster is actually part of an even larger structure. The Virgo cluster, the local group, and everything in between, along with several other superclusters, all belong to a single enormous gravitational basin of attraction. The researchers named this structure Laniakea, a Hawaiian word meaning immense heaven. Laniakea spans 520 million light-years. It contains approximately 100,000 large galaxies. Its total mass is roughly 100 million billion times the mass of our central star. To put that in perspective, if our star were a grain of sand, Laniakea would weigh more than Earth's entire biosphere. The Virgo cluster sits at one edge of Laniakea, pulling the local group toward it. But Laniakea has its own center of mass, a region of space toward which all the galaxies in the supercluster are slowly falling. This gravitational center is called the Great Attractor, and it sits roughly 200 million light-years away from us. The Great Attractor is partially hidden behind the Milky Way's disk, in the zone of avoidance where dust blocks our view. But astronomers have mapped it using infrared and radio observations, revealing a massive concentration of galaxy clusters moving together through space. Everything in Laniakea, including us, is being pulled toward this gravitational focal point. But the story does not end there. Laniakea itself is moving. It is being pulled toward an even more massive structure called the Shapley supercluster, located approximately 650 million light-years away. Shapley contains tens of thousands of galaxies and is one of the most massive structures in the observable universe. This reveals a hierarchy of cosmic structures. Stars cluster into galaxies. Galaxies cluster into groups. Groups cluster into clusters. Clusters cluster into superclusters. And superclusters themselves move in response to even larger concentrations of matter, creating a cosmic web of structure spanning billions of light-years. The Virgo cluster, which seemed so dominant in our local region of space, is just one node in this vast network. Its gravity shapes our motion, but it is itself shaped by structures beyond. Laniakea is almost too large to comprehend. 520 million light-years across 100,000 galaxies, mass equivalent to 100 million billion stars. These numbers are so vast that they lose meaning. The human brain did not evolve to grasp scales like this. To understand Laniakea, imagine starting with something familiar. Take our solar system. Now expand outward to the nearest stars. Now keep expanding to encompass the entire Milky Way. Now include the local group. Now the Virgo cluster. You are still not even close to the full extent of Laniakea. You would need to expand thousands of times farther, encompassing dozens of galaxy clusters and hundreds of galaxy groups, before reaching its boundaries. Laniakea is not a spherical structure. It has a complex shape, with filaments of galaxies stretching between major clusters and vast voids where few galaxies exist. Think of it as a web or network with dense nodes connected by strands and large empty regions in between. This structure is not accidental. It reflects how gravity shaped the universe over billions of years. In the early universe, matter was distributed almost uniformly, with only tiny variations in density. But those tiny variations were enough. Regions that were slightly denser had slightly more gravity, which attracted surrounding matter, making them even denser. Over billions of years, this process amplified the initial tiny differences into the large-scale structure we see today. Dense regions became denser, eventually forming galaxies and galaxy clusters. The regions between them became voids, losing matter to the surrounding structures. The result is a cosmic web, filaments and sheets of galaxies surrounding vast empty spaces. Laniakea is one section of this web. The name Laniakea, meaning immense heaven, was chosen by the astronomers who mapped this supercluster because Hawaiian navigators traditionally used the night sky to guide their journeys across the Pacific Ocean. In a sense, modern astronomers are doing the same thing, using the stars to map their position in the cosmos. Laniakea contains several major substructures. The Virgo supercluster, which includes the local group, is one appendage. The Hydra Centaurus supercluster is another. The Pavo Indus supercluster forms a third component. These structures, which were once thought to be separate superclusters, are now understood as parts of the larger Laniakea system, all falling toward the same gravitational center. That center, the Great Attractor, dominates the dynamics of the entire supercluster. Located in the direction of the constellation Centaurus, it consists of several massive galaxy clusters, including the Norma cluster and the Centaurus cluster. The combined mass of these clusters creates a gravitational well so deep that everything within hundreds of millions of light-years feels its pull. Our motion toward the Great Attractor adds up to roughly 370 miles per second when you account for all the various gravitational influences on the local group. We have been falling toward it for billions of years, and we will continue falling for billions more. Eventually, if no other forces intervene, the local group might become part of one of the massive clusters near the Great Attractor. But there is a catch. The universe is not just expanding, it is accelerating. Dark energy, a mysterious force that permeates all of space, is pushing galaxies apart at an ever-increasing rate. This expansion works against gravity, pulling structures apart even as gravity tries to hold them together. On small scales, gravity wins. The Milky Way will not be torn apart by dark energy. Neither will the local group or even the Virgo cluster. These structures are bound tightly enough that their internal gravity overcomes the expansion of space. But on the scale of Laniakea, dark energy dominates. Laniakea is not gravitationally bound. The supercluster is, in fact, slowly dissolving. The expansion of space is pushing its most distant components apart, faster than they can fall together. Over tens of billions of years, Laniakea will fragment, its member clusters receding from each other until they can no longer be considered part of the same structure. This is the eventual fate of all superclusters. Dark energy will win. The only gravitationally bound structures that will survive into the far future are individual galaxy clusters and groups. Everything else will be pulled apart by the accelerating expansion of space. For now, though, Laniakea remains coherent enough to map and study. It represents the local cosmic environment, the largest structure to which we meaningfully belong. When we say we live in the Milky Way, in the local group, in the Virgo supercluster, in Laniakea, we are giving our complete cosmic address, our position in the hierarchy of structures that make up the universe. But even Laniakea, as immense as it is, occupies only a tiny fraction of the observable universe. The structures beyond it are even more staggering. Hidden behind the Milky Way, obscured by dust and starlight, lies a gravitational anomaly that has puzzled astronomers for decades. It is called the Great Attractor, and its pull is reshaping our entire region of the universe. The story of its discovery begins in the 1970s, when astronomers mapped the motions of galaxies in our cosmic neighborhood. They expected to find a relatively simple pattern, galaxies moving away from each other due to the expansion of the universe, with small random motions from local gravitational interactions. Instead, they found something strange. Hundreds of galaxies, including the Milky Way, were all moving in the same direction at speeds of several hundred miles per second. This was not the expansion of space. This was a bulk flow, a massive scale motion of matter towards some distant point. The direction of this motion pointed toward a region of sky in the constellation Centaurus, in the southern sky as viewed from Earth. But that region is located behind the Milky Way's disk, in the zone of avoidance, where thick clouds of dust and gas block visible light. Whatever was causing this motion remained hidden from view. Astronomers dubbed this mysterious gravitational center the Great Attractor. They estimated it must have a mass equivalent to tens of thousands of galaxy masses to produce the observed motions. But for years, they could not directly observe it because of the obstruction. Breakthroughs came when astronomers used infrared and radio observations, which can penetrate dust clouds that block visible light. These observations revealed a complex structure of galaxy clusters roughly 200 million light-years away. The Norma cluster, the Centaurus cluster, and several other massive concentrations of galaxies create a gravitational focal point, pulling on everything around it. The Great Attractor is not a single object. It is a region of space where multiple galaxy clusters are concentrated, creating a combined gravitational pull far stronger than any individual cluster. Think of it as a valley in the cosmic landscape. Galaxies slide downhill toward it, accelerating as they approach. Our motion toward the Great Attractor occurs at roughly 370 miles per second. This is separate from our motion toward the Virgo cluster and separate from the Milky Way's approach to Andromeda. All these motions add together like vectors, creating a complex three-dimensional path through space. What makes the Great Attractor particularly intriguing is that it is not the only massive structure affecting our motion. Beyond it, at a distance of approximately 650 million light-years, lies the Shapley supercluster, an even more massive concentration of galaxies. The Shapley supercluster contains tens of thousands of galaxies spread across several major clusters. Its total mass is estimated at more than 10,000 trillion times the mass of our central star. The Shapley supercluster exerts its own gravitational influence on our motion. Some astronomers argue that what we call the Great Attractor is actually just an intermediate waypoint, and the true destination of our cosmic journey is the Shapley supercluster. In this view, the Great Attractor is important, but it is part of a larger flow pattern spanning even greater distances. Mapping these large-scale motions has revealed something profound about the universe. Structure exists on all scales. Just as planets orbit stars, and stars orbit galactic centers, and galaxies cluster into groups, those groups themselves move in response to even larger structures. There appears to be no ultimate scale at which the universe becomes uniform and structureless, at least not on scales smaller than billions of light-years. The Great Attractor represents one of the largest structures influencing our motion. It is a gravitational giant, a concentration of matter so massive that it shapes the trajectories of galaxies hundreds of millions of light-years away. We are falling toward it, pulled by gravity across distances so vast that light takes hundreds of millions of years to cross them. But this motion will not continue forever. As mentioned earlier, the accelerating expansion of space will eventually overcome these gravitational attractions. The Great Attractor will not ultimately attract most of the galaxies currently moving toward it. Dark energy will win. The galaxies will slow their approach, stop, and then begin receding as space expands between them. This is already happening on the largest scales. The most distant clusters in Laniakea are already receding from each other faster than they are falling together. Over tens of billions of years, Laniakea will dissolve completely. The Virgo cluster will become isolated, no longer connected to the other clusters that currently share its supercluster. The Great Attractor will become the Great Isolator, surrounded by empty space as dark energy pushes everything beyond a certain distance out of reach forever. For now, though, its pull remains real and measurable. We are falling toward it, have been for billions of years, and will continue for billions more. It is one of the largest structures shaping our cosmic destiny. But there are structures in the universe that dwarf even the Great Attractor. Imagine a galaxy so large that if you placed it where the Milky Way sits, it would stretch past the Andromeda galaxy, past the Triangulum galaxy, past every member of the local group, reaching into intergalactic space beyond. This is not science fiction. This galaxy exists. It is called IC 1101, and it is one of the largest galaxies ever discovered. IC1101 lies approximately 1.15 billion light-years from Earth in the constellation Virgo. It sits at the center of the Abell 2029 galaxy cluster, a massive collection of galaxies bound together by gravity. The galaxy is classified as a supergiant elliptical, meaning it lacks the spiral arms and disk structure of galaxies like the Milky Way. Instead, it is a three-dimensional swarm of stars in an elongated, roughly egg-shaped distribution. The numbers associated with IC1101 are staggering. Its diameter spans approximately 400,000 to 550,000 light-years, depending on how the measurement is made. That is 4 to 5 times wider than the Milky Way. But diameter alone does not capture its true scale. The galaxy is surrounded by an enormous halo of faint starlight, extending as much as 2 million light-years from its core. IC1101 contains roughly 100 trillion stars. That is 250 to 500 times more stars than the Milky Way. If you could count one star per second, it would take over 3 million years to count them all. The total mass of IC1101, including dark matter, is estimated at several times that of the Milky Way. Much of this mass is in the form of dark matter surrounding the visible galaxy, providing the gravitational glue that holds this immense structure together. At the center of IC1101 sits a supermassive black hole with a mass estimated at 40 to 100 billion times that of our central star. This black hole is not currently very active, but if it were feeding on matter, it would create a quasar visible across half the universe. How did IC1101 become so large? The answer lies in its position at the center of a galaxy cluster. Over billions of years, it has consumed dozens, perhaps hundreds, of smaller galaxies that ventured too close. Each merger added more stars to IC1101, gradually building it into the monster it is today. Galaxy clusters are violent environments. Galaxies there move at speeds exceeding 1 million miles per hour, orbiting around the cluster's center of mass. When two galaxies pass close to each other, tidal forces can rip them apart. The largest galaxy at the cluster center, known as the brightest cluster galaxy, acts like a gravitational trap, gradually accumulating matter from these interactions. IC1101 is a brightest cluster galaxy. It sits at the gravitational center of Abell 2029, surrounded by hundreds of other galaxies that orbit around it. Over cosmic timescales, many of these smaller galaxies will eventually be consumed, adding their stars to IC1101 and making it even larger. The galaxy's star population is old. IC1101 contains mostly red and yellow stars, indicating that star formation ceased long ago. Unlike spiral galaxies, which continuously form new stars from gas clouds in their disks, elliptical galaxies, like IC1101, have consumed or expelled most of their gas. Without raw materials for new stars, the galaxy is slowly fading, its existing stars gradually burning out. This gives IC1101 a bleak future. Its stars will age and die over trillions of years, and no new stars will replace them. Eventually, the galaxy will become a vast collection of stellar remnants, white dwarfs, neutron stars, and black holes drifting through space in darkness. But that fate lies trillions of years in the future. For now, IC1101 remains one of the most impressive structures in the known universe. Its sheer size challenges our assumptions about how large galaxies can grow. Theoretical models suggest there should be a limit to galaxy size, beyond which gravity cannot hold structures together against the disruptive effects of tidal forces and the expansion of space. IC1101 approaches that limit. Galaxies significantly larger than this are extremely rare, suggesting that we are seeing something close to the maximum possible size for a gravitationally bound collection of stars. For comparison, if you placed IC1101 next to the Milky Way, our galaxy would look like a dwarf. If both galaxies were countries, IC1101 would be Russia and the Milky Way would be France. The size difference is that dramatic. Yet, even IC1101 is tiny compared to the larger structures in the universe. Its 400,000 light-year diameter is less than 1% the size of Laniakea. Galaxies, even the largest ones, are like specks within the much larger structures of superclusters and the cosmic web. Still, IC1101 represents the upper limit of what a single gravitationally bound object can become. It is a monument to cosmic time and gravity, a structure billions of years in the making, containing the remnants of hundreds of former galaxies now merged into one. And somewhere in that vast collection of 100 trillion stars, there might be planets, there might be civilizations. If beings exist there, their night sky must be spectacular, filled with the light of neighboring stars, packed far more densely than in our region of the Milky Way. But we will never know. IC 1101 is over 1 billion light-years away, far beyond the reach of any conceivable spacecraft. Galaxies are not static objects frozen in space. They move, they interact, and they collide. When two massive galaxies meet, the result is one of the most spectacular events in the cosmos. A galactic merger lasting hundreds of millions of years and completely transforming both participants. Contrary to what you might expect, galactic collisions do not involve stars crashing into each other. Galaxies are mostly empty space. The distances between stars are so vast that when two galaxies pass through each other, the probability of actual stellar collisions is almost zero. 200 billion stars can pass through another 200 billion stars with barely any direct impacts. But even though stars rarely collide, galaxies certainly do. What collides is the gravitational fields. As two galaxies approach, their mutual gravity begins distorting both structures. Stars in the outer regions get pulled toward the other galaxy. Long tidal tails of stars stream outward, stretching hundreds of thousands of light-years into space. The first pass-through is dramatic. The galaxies interpenetrate, their stars and gas clouds mixing together. Gas clouds do collide because they are large and diffuse. These collisions compress the gas, triggering enormous bursts of star formation. Thousands of new stars ignite simultaneously, creating brilliant starburst regions that outshine entire normal galaxies. After the first pass, gravity pulls the galaxies back together. They collide a second time, then a third. With each collision, orbital energy is lost to friction and tidal effects. The galaxies gradually spiral closer, their cores eventually merging into a single massive nucleus. The entire process takes roughly 1 billion years from first approach to final merger. During this time, the original structures are destroyed, spiral arms are disrupted, dust lanes are heated and dispersed. The organized rotation of spiral galaxies is scrambled into the chaotic motion of an elliptical galaxy. This is how giant elliptical galaxies like IC 1101 form. They are the products of multiple mergers between smaller galaxies, each collision adding more stars and building a larger structure. The biggest elliptical galaxies have likely experienced dozens of major mergers over their lifetimes. Astronomers can observe galactic mergers at all stages. Some galaxies are just beginning to interact, their structures still intact, but showing slight distortions. Others are in the midst of collision, with long tidal tails and bright starburst regions marking the chaos. Still others are nearly finished merging, appearing as misshapen elliptical galaxies with faint shells and streams of stars marking their violent past. One famous example is the antennae galaxies, two spiral galaxies caught in the act of merging about 70 million light-years from Earth. Long antenna-like tails of stars extend from both galaxies, giving them their name. Between the galaxies, bright pink and blue regions mark areas of intense star formation triggered by colliding gas clouds. Another example is NGC 6240, a pair of galaxies so deeply merged that they appear as a single chaotic structure. Infrared observations reveal two supermassive black holes at the center, the former cores of the two original galaxies, now spiraling toward each other. Eventually, these black holes will merge, releasing a burst of gravitational waves. The Milky Way's future collision with Andromeda will follow this same pattern. First approach in about 4 billion years. Multiple passes over the next billion years. Gradual merger into a single elliptical galaxy that astronomers have nicknamed Milky Way. During the merger, the night sky as seen from Earth will transform. Andromeda will grow larger, eventually filling much of the sky. The Milky Way's structure will become distorted and eventually unrecognizable. New stars will form in enormous numbers as gas clouds collide. The combined light from these new stars could make the night sky bright enough to read by, even without artificial light. But individual stars, including our own, will likely survive unharmed. The solar system might be flung into a different orbit, possibly into the outer regions of the merged galaxy or even out into intergalactic space. But the chances of our star actually colliding with another star remain vanishingly small. Supermassive black holes at galactic centers survive and merge during these collisions. When two supermassive black holes spiral together, they emit gravitational waves, ripples in space-time itself. These waves carry away energy, causing the black holes to gradually approach each other until they finally merge in a fraction of a second, creating a single more massive black hole. Galactic mergers are more common in the past than today. In the early universe, when galaxies were closer together and the cosmos was more crowded, mergers happened frequently. Many galaxies experienced multiple mergers, growing rapidly through accretion. Today, the universe has expanded enough that galaxies are more spread out, and mergers are less frequent, but they still occur, especially in galaxy clusters, where galaxies are packed more densely. The center of every rich galaxy cluster contains a brightest cluster galaxy that has grown by cannibalizing its neighbors. These monsters continue growing, adding more stars with each merger, becoming larger and more massive over time. Galactic mergers are violent, transformative events that reshape structures containing hundreds of billions of stars. Yet they unfold slowly enough that any civilizations present would have millions of years to observe and study the process. While IC 1101 represents the upper limit of galactic size, there exist galaxies at the opposite extreme, tiny collections of stars barely large enough to qualify as galaxies at all. Some contain only a few thousand stars. They are called ultra-faint dwarf galaxies, and their very existence is puzzling. Consider Segway 2, a dwarf galaxy orbiting the Milky Way at a distance of roughly 115,000 light-years. It contains approximately 1,000 stars spread across a region about 500 light-years across. 1,000 stars. Most globular clusters, which are dense balls of stars within galaxies, contain more stars than that. What makes Segway 2 a galaxy rather than a cluster is dark matter. Observations of stellar motions reveal that Segway 2 must be embedded in a dark matter halo roughly 1 million times the mass of our central star. This invisible matter provides the gravitational binding that holds the galaxy together. Without it, the stars would disperse into space. Segway 2 is extraordinarily faint, with a total brightness only 900 times that of our star. The Milky Way, by comparison, is 20 billion times brighter. If you could somehow transport Segway 2 to replace our central star in the sky, it would appear dimmer than the full moon. Ultra-faint dwarfs, like Segway 2, pose a problem for our understanding of galaxy formation. According to theory, the early universe was hot and filled with high-energy radiation. This radiation should have heated gas in small galaxies, blowing it away and preventing star formation. Galaxies as small as Segway 2 should have been sterilized, unable to form even the few stars they possess. Yet they exist, and not just a few of them. Astronomers have discovered dozens of ultra-faint dwarfs orbiting the Milky Way and Andromeda. Each contains somewhere between a few hundred and a few 100,000 stars, all of them old. These galaxies stopped forming stars more than 10 billion years ago, shortly after the Big Bang, and have simply coasted through space unchanged ever since. They are fossils from the early universe, pristine examples of what the first galaxies might have looked like. Their stars formed from gas that contained almost no elements heavier than hydrogen and helium, because not enough time had passed for earlier generations of stars to create and disperse heavy elements through supernova explosions. Another remarkable dwarf galaxy is Andromeda 35, discovered orbiting Andromeda at a distance of about 3 million light-years. It is roughly 1/1,000,000th the mass of the Milky Way, and so faint that it was detected only recently despite being relatively nearby. Describing it as faint hardly captures the reality. It is dimmer than a single candle viewed from thousands of miles away. These ultra-faint galaxies raise fascinating questions about dark matter. They are the most dark matter-dominated objects known. In normal galaxies, dark matter outweighs ordinary matter by a factor of 5 or 6 to 1. In ultra-faint dwarfs, that ratio can reach 1,000 to 1 or more. They are essentially dark matter structures with a few stars sprinkled in, the dark matter doing almost all the gravitational work. Why did these tiny galaxies survive when theory suggests they should not have? One possibility is that they formed very early, before the universe became fully ionized. In the first few 100 million years after the Big Bang, neutral hydrogen filled space. This hydrogen could shield small galaxies from the intense radiation that came later, allowing them to form stars before the radiation arrived to blow away their gas. Another possibility is that ultra-faint dwarfs are survivors of a larger population that has since been destroyed. For every dwarf we see, there might have been dozens or hundreds that did not survive, torn apart by tidal forces or consumed by larger galaxies. The ones we observe might simply be the lucky ones. The Milky Way likely has many more ultra-faint dwarfs orbiting it that remain undiscovered. They are so dim that detecting them requires carefully analyzing astronomical survey data, looking for slight overdensities of stars in particular regions of the sky. Each new generation of telescopes reveals a few more, but many probably lurk beyond our current detection limits. Some ultra-faint dwarfs are not just faint, but also incredibly diffuse. Crater 2, another Milky Way satellite, spreads its stars across a region over 7,000 light-years in diameter despite containing fewer than 1 million stars. Its stars are so spread out that the galaxy is barely distinguishable from the background. It is like cosmic fog, barely there. These tiny galaxies provide crucial tests for dark matter theories. Because they are so dominated by dark matter, studying their structure and dynamics reveals properties of dark matter that are difficult to detect in larger galaxies, where ordinary matter plays a bigger role. They also represent the smallest building blocks of cosmic structure. In hierarchical models of galaxy formation, small galaxies formed first, then merged over time to build larger galaxies. Ultra-faint dwarfs might be leftovers from this early era, the last survivors of the first generation of galaxies, too small to merge with anything else, simply orbiting larger galaxies and slowly fading as their stars age. They are ghosts of the early universe, reminders that galaxies come in all sizes, from monsters like IC 1101 to specks like Segway 2, with the Milky Way somewhere in between. Everything we have discussed so far, every galaxy and star, every structure visible in telescopes, represents only about 15% of the matter in the universe. The remaining 85% is dark matter, and we cannot see it at all. Dark matter does not emit light. It does not absorb light. It does not reflect light. It does not interact with electromagnetic radiation in any detectable way. We know it exists only through its gravitational effects on ordinary matter. The first hints of dark matter came in the 1930s, when astronomer Fritz Zwicky studied the Coma cluster of galaxies. He measured the speeds at which galaxies moved within the cluster and calculated how much mass would be needed to hold the cluster together gravitationally. The answer shocked him. There had to be roughly 400 times more mass than could be accounted for by visible stars. Zwicky proposed that most of the cluster's mass must be dark, invisible to telescopes. His colleagues were skeptical. The idea of invisible matter sounded too strange, too much like inventing something to fix a problem with the observations. But more evidence accumulated over the decades. In the 1970s, astronomer Vera Rubin studied the rotation curves of spiral galaxies. She measured how far stars orbited at different distances from galactic centers. According to Newton's laws, stars farther from the center should orbit slower, just as outer planets in our solar system orbit slower than inner planets. Instead, Rubin found that stars in the outer regions of galaxies orbit just as fast as stars closer to the center. This flat rotation curve defied expectations. The only explanation was that galaxies contain vast halos of invisible matter extending far beyond the visible disk, providing additional gravitational pull that keeps outer stars moving fast. Today, evidence for dark matter is overwhelming. It shows up in galaxy rotation curves, in the motions of galaxies within clusters, in gravitational lensing, where light from distant objects is bent by invisible mass, and in the cosmic microwave background radiation from the early universe. Every observation points to the same conclusion. Most of the matter in the universe is dark. What is dark matter made of? We do not know. It is not ordinary matter made of protons, neutrons, and electrons. It is something else entirely. Some type of particle that interacts with ordinary matter only through gravity. Leading theories suggest it might be exotic particles like WIMPs, weakly interacting massive particles, or axions. But decades of searching have not yet produced a confirmed detection. What we do know is how dark matter is distributed. Computer simulations show that dark matter forms vast halos around galaxies, with higher concentrations at the center, gradually declining toward the edges. These dark matter halos extend far beyond the visible stars, potentially reaching hundreds of thousands of light-years from galactic centers. The Milky Way sits within a dark matter halo roughly 600,000 light-years across. containing a total mass perhaps 10 times that of all the visible stars combined. This halo provides the gravitational scaffolding that holds the galaxy together. Without it, the Milky Way would fly apart. The stars orbit too fast to be held together by the gravity of ordinary matter alone. Dark matter also shaped the formation of galaxies. In the early universe, dark matter clumped together first, creating gravitational wells into which ordinary matter fell. Gas collected in these dark matter halos, cooled, and eventually formed stars. Every galaxy formed inside a pre-existing dark matter structure. On the largest scales, dark matter forms the cosmic web. Simulations of the universe's evolution show dark matter forming vast filaments connecting galaxy clusters with enormous voids in between. This structure emerged naturally from the initial tiny density variations in the early universe, amplified over billions of years by gravitational attraction. Ordinary matter follows the dark matter, collecting in the same filaments and nodes. This is why galaxies are arranged in a web-like pattern rather than being randomly distributed. The visible structure of the universe is a map of the underlying dark matter distribution. Dark matter even affects individual stars. The Milky Way's dark matter halo likely contains billions of times the mass of our central star in dark matter, and some of that dark matter passes through our solar system, through Earth, and through your body right now. Countless dark matter particles are streaming past you every second, undetected because they interact only through gravity. Despite our ignorance about what dark matter is, we can calculate its properties. It must be cold, meaning it moves slowly compared to the speed of light. It must be stable, not decaying into other particles quickly, and it must clump together on large scales while remaining diffuse on small scales, matching the observed structure of galaxies and galaxy clusters. Dark matter is one of the greatest mysteries in modern physics. We know it is there. We know how much there is. We know how it is distributed, but we do not know what it actually is. Solving this mystery is one of the most important goals in physics today, with experiments running deep underground and in space, searching for dark matter particles. For now, dark matter remains invisible, detectable only through its gravitational fingerprints on the cosmos. It is the hidden architecture of the universe, the scaffolding on which everything visible is built, including the Milky Way, the local group, and all the structures we have explored. Step back, zoom out from the Milky Way, past Andromeda, past the local group, past the Virgo cluster, past Laniakea. Keep going until you can see the full extent of everything we can possibly observe. What you find is staggering. Approximately 2 trillion galaxies filling a sphere 93 billion light-years across. 2 trillion. That number is difficult to grasp. If you could count one galaxy per second, it would take over 63,000 years to count them all. And each of those galaxies contains hundreds of millions to hundreds of billions of stars. The total number of stars in the observable universe is estimated at around 1 septillion, a 1 followed by 24 zeros. These galaxies are not evenly distributed. They cluster into groups and clusters, which cluster into superclusters, which form filaments and walls surrounding vast cosmic voids. The largest structures span hundreds of millions of light-years. The largest known structure, the Hercules Corona Borealis Great Wall, stretches roughly 10 billion light-years across, though its status as a true connected structure is debated. Most galaxies in the universe are dwarf galaxies, small and faint with fewer than 10 billion stars. Massive spirals like the Milky Way and giant ellipticals like IC 1101 are relatively rare. If you selected a galaxy at random from the universe, you would most likely pick a dwarf. The farthest galaxies we can see are over 13 billion light-years away. We see them as they were more than 13 billion years ago, when the universe was less than 1 billion years old. These ancient galaxies are small and irregular, the first generation of star-forming structures emerging from the primordial gas that filled the early cosmos. Between us and those distant galaxies lie countless others at every possible distance. Light from these galaxies has been traveling through space for different amounts of time, some for millions of years, some for billions, some for more than 10 billion years. When we look at the deep universe, we are seeing galaxies not as they are now, but as they were at various points in cosmic history. This is one of the most profound facts about astronomy. Looking out in space is equivalent to looking back in time. The speed of light is finite, so information about distant objects takes time to reach us. The farther away something is, the older the light we receive from it. We are observing cosmic history spread out before us in space. The James Webb Space Telescope, launched in 2021, has pushed our view even deeper, detecting galaxies that formed only a few 100 million years after the Big Bang. These galaxies are extraordinarily distant, their light stretched by the expansion of space to infrared wavelengths invisible to the human eye but detectable with specialized instruments. Counting 2 trillion galaxies is itself an achievement requiring decades of observation. Astronomers use deep field surveys, pointing telescopes at small patches of apparently empty sky and exposing for hours or days to collect light from the faintest possible sources. These deep fields reveal galaxies so distant and dim that they appear as mere specks in the images. By counting galaxies in these deep fields and extrapolating to the entire sky, astronomers estimate the total number. The figure has increased over time as telescopes have improved. In the 1990s, estimates were around 100 billion galaxies. By 2016, that figure had increased to 2 trillion when very faint galaxies were included in the count. This means the universe is even more crowded than previously thought. And these 2 trillion galaxies exist only in the observable universe, the region from which light has had time to reach us since the Big Bang. The total universe, including regions we cannot see because their light has not yet had time to arrive, is likely far larger. It might be infinite. Every one of these 2 trillion galaxies is a structure like the Milky Way, a collection of hundreds of millions or billions of stars, many with their own planets, some possibly harboring life. The sheer number of possible worlds is almost incomprehensible. Even if planets suitable for life are rare, with 2 trillion galaxies each containing billions of stars, the total number of potentially habitable planets must be astronomical. This makes the silence from the cosmos all the more mysterious. With so many galaxies, so many stars, so many potential worlds, where is everyone? This question, known as the Fermi paradox, has no satisfactory answer. Perhaps life is extremely rare. Perhaps intelligent life is even rarer. Perhaps civilizations destroy themselves before becoming spacefaring. Or perhaps space is simply too vast and interstellar distances too great for civilizations to ever meet. The 2 trillion galaxies also represent 2 trillion separate island universes, each with its own history, its own populations of stars and planets, its own story. Most of these galaxies will never be studied in detail. They are too far, too faint, too numerous. We can count them, observe their general properties, and study their distribution, but we will never know their individual characteristics. This is the observable universe, a vast collection of structures, each itself vast beyond comprehension, spread across distances that light takes billions of years to traverse. And all of it, every galaxy, every star, every planet, emerged from a state of incredibly high density and temperature roughly 13.8 billion years ago. How such a universe came to exist, why it has the properties it does, and what its ultimate fate will be are questions that push the boundaries of human knowledge. The observable universe has a diameter of approximately 93 billion light-years. Read that number again, 93 billion. And here is where things become strange. The universe is only 13.8 billion years old. At first, this seems impossible. If the universe is 13.8 billion years old and nothing can travel faster than light, then the farthest we should be able to see is 13.8 billion light-years in any direction. The observable universe should be only 27.6 billion light-years across, not 93 billion. The resolution to this paradox lies in understanding that space itself expands. When we say the universe is expanding, we do not mean galaxies are moving through space away from each other, like shrapnel from an explosion. We mean that space itself is stretching, creating new distance between objects, even though those objects are not actually moving. Consider a galaxy that emitted light 13 billion years ago. That light has been traveling toward us ever since, crossing space at 671 million miles per hour. But while the light was traveling, the space it was moving through was expanding. The galaxy that emitted the light has been carried away from us by that expansion. Today, that galaxy is not 13 billion light-years away. It is approximately 30 billion light-years away. The light has traveled 13 billion light-years through space, but the galaxy itself has moved much farther during those 13 billion years because space was expanding the entire time. This is why the observable universe is 93 billion light-years across. We can see light from objects that are now 46.5 billion light-years away in any direction, even though that light has been traveling for less than the age of the universe. The expansion of space has carried those objects farther away during the time their light was reaching us. The edge of the observable universe is not a physical boundary. It is simply the farthest distance from which light has had time to reach us since the Big Bang. Beyond that edge, there is more universe. There are more galaxies, more stars, more planets, but we cannot see them because their light has not yet had time to arrive. Every year, the observable universe grows by approximately 1 light-year in radius. New regions of space enter our observable sphere as light from more distant objects finally reaches us. You might think this means we will eventually be able to see everything, given enough time, but the opposite is true. The expansion of space is accelerating. This acceleration is driven by dark energy, a mysterious force that pervades all of space and pushes things apart. Because of this acceleration, most galaxies beyond our local neighborhood will eventually recede from us faster than the speed of light. This does not violate relativity. Nothing is moving through space faster than light, but space itself can expand at any rate. There is no speed limit on the expansion of space itself. As space expands faster and faster, galaxies are carried along with it, receding from us at speeds that eventually exceed the speed of light. Once a galaxy is receding faster than light, no light it emits can ever reach us. The photons try to travel toward us, but the space between us is expanding so fast that the photons never get closer. They are like someone running on a treadmill that is moving backward faster than they can run forward. This creates a cosmic event horizon, a boundary beyond which events can never affect us. Galaxies beyond this horizon are forever cut off. We will never see them, never receive signals from them, never have any causal interaction with them. They might as well not exist, as far as we are concerned. Currently, this cosmic event horizon sits approximately 16 billion light-years away. Galaxies farther than this are already unreachable. Light leaving those galaxies today will never arrive here, no matter how long we wait. The photons will travel through space forever, never gaining ground against the expansion carrying their source galaxies away. Over time, this horizon will move closer. Galaxies that are currently within reach will cross the horizon and disappear from view. Eventually, only the galaxies in our local group will remain visible. Everything else will have receded beyond the cosmic horizon, their light redshifted into undetectability. Trillions of years from now, the observable universe as seen from the Milky Way will consist only of the merged remains of our local group of galaxies, surrounded by empty darkness. Future civilizations arising at that time will look out and see nothing beyond their own galaxy. They will have no evidence that 2 trillion other galaxies exist. They will not know about the cosmic web, about superclusters, about the expansion of space. We are living in a special time, a cosmic moment when the universe is old enough to have formed structures like galaxies and stars, but young enough that we can still observe the larger cosmos. Future inhabitants of the universe will not have this opportunity. The accelerating expansion will rob them of the view. The 93 billion light-year diameter of the observable universe represents the full extent of everything we can possibly know about through direct observation. Beyond this lies the unobservable universe, forever hidden from view. It might be infinite. It might contain an infinite number of galaxies. We will never know. This is both humbling and profound. The observable universe, as vast as it is likely just a tiny fraction of the total universe. Everything we have discussed, every galaxy and structure we have explored, exists in what might be an infinitesimally small portion of reality. If you could view the entire observable universe from outside, zooming back far enough to see its largest structures, you would notice something remarkable. Galaxies are not randomly scattered through space. They are arranged in a vast, web-like pattern, forming filaments and sheets that surround enormous empty voids. This is the cosmic web, the largest scale structure in the universe. It spans billions of light years and contains virtually all the matter and galaxies in the cosmos. Understanding this structure reveals how the universe evolved from its smooth beginning to its current complex state. The cosmic web formed through gravitational amplification of tiny initial variations in density. In the very early universe, shortly after the Big Bang, matter was distributed almost uniformly. But almost is the key word. There were tiny fluctuations, regions slightly denser or less dense than average, with differences of only about 1 part in 100,000. Over time, gravity amplified these tiny differences. Slightly denser regions had slightly more gravity, which attracted surrounding matter, making them denser still. This positive feedback continued for billions of years. Dense regions became denser, pulling matter away from the less dense regions between them. The result is a network of filaments where matter is concentrated, surrounding vast voids where almost no galaxies exist. The filaments are like threads in a web, with galaxy clusters forming at the intersections where multiple filaments meet. The voids are roughly spherical regions, typically 100 to 300 million light-years across, containing very few galaxies. The largest filaments are extraordinary structures. The Sloan Great Wall, discovered in 2003, is a chain of galaxy clusters and superclusters stretching approximately 1.4 billion light-years across. It contains tens of thousands of galaxies arranged along a relatively thin sheet. The CFA 2 Great Wall, discovered earlier in 1989, stretches roughly 750 million light-years across. The Hercules Corona Borealis Great Wall, mentioned earlier, might span 10 billion light-years, though whether it represents a single connected structure is debated among astronomers. These walls and filaments are not solid structures. They are more like highways of galaxies, regions of space where galaxies are much more common than average. The galaxies within them are still separated by millions of light-years, but they are far closer together than galaxies in voids or in the general field. The voids between the filaments are not completely empty, but they are close. A typical void might contain only a handful of galaxies, or perhaps dozens in a region where a rich cluster would contain thousands. The density of galaxies in voids is roughly 1/10 the average density of the universe. Interestingly, the galaxies in voids tend to be small, blue, and actively forming stars. This contrasts with galaxies in clusters, which tend to be large, red, and have ceased forming new stars. The difference arises from the environment. Cluster galaxies experience frequent interactions that strip away their gas and disrupt star formation, while void galaxies evolve in isolation, retaining their gas and continuing to form stars. The cosmic web structure is not unique to galaxies. Dark matter follows the same pattern, forming vast filaments and halos surrounding the voids. In fact, the dark matter web formed first, with ordinary matter simply following the gravitational pull of the dark matter structures. Computer simulations can reproduce the cosmic web structure, starting from initial conditions shortly after the Big Bang and letting gravity do its work. These simulations show filaments forming naturally as matter flows toward higher density regions, eventually creating a structure remarkably similar to what we observe in the real universe. The filaments themselves have internal structure. Matter flows along them like water through pipes, gradually migrating toward the galaxy clusters at the filament intersections. This flow continues today, with galaxies slowly moving along the filaments toward the nearest major cluster. Some astronomers describe the cosmic web as the skeleton of the universe, the fundamental organization underlying all structure. Everything exists within this framework. Individual galaxies, galaxy groups, clusters, superclusters, all are components of the larger web pattern. The web also defines the large-scale motion of matter. Galaxies move along the filaments, flowing toward the nodes where clusters form. The Great Attractor, which we discussed earlier, is one such node where multiple filaments converge, creating a region of enhanced gravitational pull. On the very largest scales, approaching the size of the observable universe, the web structure begins to fade. At distances of several billion light-years, the universe starts to look statistically uniform. This is the cosmological principle in action. On large enough scales, the universe is homogeneous and isotropic, appearing roughly the same in all directions. But on scales smaller than a billion light-years, the cosmic web dominates. It is the organizing principle of the universe, the pattern that emerges when gravity shapes matter over cosmic time. Every galaxy in the universe, including the Milky Way, exists somewhere within this web, following paths defined by the distribution of matter around it. The web will not last forever. As dark energy continues accelerating the expansion of space, the filaments will gradually stretch and thin. Galaxies will recede from each other, carried by the expansion. Eventually, the web will dissolve completely, leaving only isolated galaxy groups floating in an ever-expanding void. But that fate lies trillions of years in the future. For now, the cosmic web remains the defining feature of large-scale cosmic structure. Return now from the vast scales of the cosmic web to something more local, our exact position within the Milky Way. Where are we? Not metaphorically, but precisely. Which part of the galaxy do we inhabit? We are located approximately 27,000 light-years from the galactic center. This places us roughly 40% of the way out from the center to the edge, in what astronomers call the galactic disk. We are neither in the dense central regions, nor in the sparse outer reaches. We occupy a middle zone, typical of spiral galaxy disks. More specifically, we sit on the inner edge of the Orion Arm, also called the Orion Spur. This is a minor spiral arm, smaller than the four major arms that define the Milky Way's spiral structure. The Orion Arm stretches approximately 3,500 light-years long and about 1,000 light-years wide. It connects the Sagittarius Arm, which lies closer to the galactic center, and the Perseus Arm, which lies farther out. Our position within this arm is not static. We orbit the galactic center at approximately 514,000 miles per hour. But this motion is not a perfect circle. Our path wobbles slightly up and down relative to the galactic plane as we move. Currently, we are very close to the galactic plane, within about 70 light-years of the midplane. This up and down motion, called vertical oscillation, takes approximately 70 million years to complete one full cycle. We cross through the galactic plane roughly every 35 million years. Some scientists have speculated that passing through the denser midplane might increase the rate of comet impacts on Earth, potentially contributing to mass extinction events. But this remains controversial. Our location has significant implications for life on Earth. Being far from the galactic center is advantageous. The center is a crowded, high-radiation environment where supernovae are more common and the supermassive black hole occasionally flares. Planets there would be subjected to more intense radiation, making stable conditions for life more difficult. But we are not too far out either. The outer regions of the galaxy have lower metallicity, meaning fewer heavy elements are available to form rocky planets. Earth and the other rocky planets in our solar system contain significant amounts of elements like iron, silicon, and carbon that were created in previous generations of stars. In the outer galaxy, where fewer stars have lived and died, these elements are scarcer. Our position in the Orion Arm also places us between the major spiral arms. The spiral arms themselves are regions of active star formation, where massive stars are born and die in supernova explosions within relatively short timeframes. Being between the arms means we experience fewer nearby supernovae, which could otherwise bathe Earth in harmful radiation. Astronomers sometimes call our location the Galactic Habitable Zone, a region where conditions are favorable for the development of complex life. Close enough to the center that heavy elements are abundant, but far enough out that radiation levels are manageable. Between the spiral arms where supernova rates are lower, in the disk where most stars are located, but able to venture slightly above and below the plane. From our position, we have a limited view of the galaxy. When we look toward the center, we see the dense band of the Milky Way. When we look away from the center, toward the outer edge, we see fewer stars. We cannot see the full spiral structure because we are embedded within it. It is like trying to see the shape of a forest while standing among the trees. The nearest stars to us are sparse. Proxima Centauri, the closest, is over 4 light-years away. Within 10 light-years, there are only about 14 stars or star systems. Within 100 light-years, there are several thousand. We live in a relatively typical stellar neighborhood, neither particularly dense nor particularly sparse. Our location also affects which astronomical objects we can easily observe. The large and small Magellanic Clouds, dwarf galaxies orbiting the Milky Way, are visible only from the southern hemisphere because of our position in the galaxy. Similarly, the galactic center is best viewed from southern latitudes, where it passes high in the sky during parts of the year. If Earth were located on the opposite side of the galaxy, our view would be different. We might have different satellite galaxies visible in our sky. The galactic center would appear in a different constellation. The distribution of nearby stars would be different. If we were located closer to the galactic center, our night sky would be far more crowded with stars. In the inner galaxy, stars are packed more densely, and the sky would blaze with thousands of bright stars visible to the naked eye. But the increased radiation and higher frequency of catastrophic events might make complex life less likely to develop. If we were located in the outer galaxy, our sky would be darker, with fewer visible stars. The Milky Way band would be less prominent, but the lower density of heavy elements might have prevented the formation of Earth in the first place. Our position, then, is not random. It reflects a location where conditions are favorable for rocky planets, stable orbits, and the development of life over billions of years. We sit in a relatively quiet region of a typical spiral galaxy, far enough from hazards but close enough to resources. This is where we are. The Orion Arm, the galactic suburbs, a cosmic location neither too hot nor too cold, not too crowded nor too empty. A place where a planet could form, where life could arise, and where that life could eventually look up at the night sky and wonder about its place in the cosmos. There is a band across the sky, roughly 10 to 20 degrees wide, centered on the plane of the Milky Way, where our view of the universe is severely limited. Astronomers call it the zone of avoidance, and it represents one of the most frustrating blind spots in observational astronomy. The problem is dust. The Milky Way contains vast clouds of dust particles, each grain typically less than 1,000th of a millimeter across. These particles are made of carbon, silicon, and other heavy elements ejected by dying stars. Individually, they are tiny and insubstantial. Collectively, they block light. Visible light cannot penetrate thick dust clouds. The dust particles absorb and scatter blue light more efficiently than red light, causing distant objects to appear redder than they actually are. When dust is thick enough, it blocks light completely, creating dark patches in the sky where nothing can be seen. The galactic plane contains the highest concentration of dust in the Milky Way. When we look toward the plane, our line of sight passes through enormous dust clouds that block light from objects beyond. This means we cannot see through the galaxy to the universe beyond in those directions. This creates serious observational problems. There are probably thousands of galaxies hidden behind the zone of avoidance, invisible to optical telescopes. Major structures like the Great Attractor lie partially or entirely within the zone, making them difficult to study. We have an incomplete map of our cosmic neighborhood because a significant portion of it is obscured. For decades, this blind spot frustrated astronomers, but advances in infrared and radio astronomy have provided partial solutions. Infrared light, with its longer wavelength, can penetrate dust clouds that block visible light. Radio waves penetrate even better, passing through dust with minimal absorption. Using infrared telescopes, astronomers have mapped portions of the zone of avoidance, revealing galaxies and structures previously hidden. Radio observations of neutral hydrogen have traced the spiral arms of the Milky Way through regions where optical observations show nothing but darkness. X-ray observations have revealed the supermassive black hole at the galactic center, invisible in optical light. These multi-wavelength observations have dramatically improved our understanding of the hidden galaxy, but gaps remain. The very center of the Milky Way is so crowded and dust-choked that even infrared light struggles to penetrate. Our view of Sagittarius A star, the central black hole, comes entirely from radio, infrared, and X-ray observations. The zone of avoidance also affects our census of nearby galaxies. The Milky Way might have more satellite dwarf galaxies than we have detected, with some hidden behind dense star fields and dust in the galactic plane. Surveys of the local universe are incomplete in the directions where the Milky Way blocks our view. This obscuration is not uniform. Some directions through the galactic plane have less dust than others, creating windows where we can see farther. Astronomers target these windows for observations when they want to study objects beyond the Milky Way that happen to lie in those directions. The dust also affects how we perceive the Milky Way itself. The bright band we see in the night sky is not a complete view of our galaxy. We see primarily the stars close enough to us that their light can reach us despite the intervening dust. The most distant stars in the Milky Way, on the far side of the galactic center, are invisible to us. Interestingly, if an alien astronomer on a planet on the opposite side of the Milky Way were looking at us, they would face the same problem. They would see a zone of avoidance in the direction of their galactic plane, and Earth's location would lie within that zone. We would be invisible to them in optical light, hidden behind the same dust clouds that hide them from us. The zone of avoidance reminds us that our view of the universe is fundamentally limited by our position within it. We cannot step outside the Milky Way to see it clearly. We must work with what we can observe from our location, using clever techniques and multiple wavelengths to piece together a complete picture. Future observations will continue improving our view through the zone. The James Webb Space Telescope, with its powerful infrared capabilities, can see through dust better than any previous instrument. Radio telescope arrays can map hydrogen throughout the galaxy with increasing precision, Each advance reveals more of what was previously hidden, but some regions will always remain difficult to observe. The very densest dust clouds might block even infrared light. The galactic center, so crowded with stars and gas and dust, will always present observational challenges. We will never have as clear a view of those regions as we have of regions outside the galactic plane. This limitation is humbling. Despite all our technological advances, despite telescopes that can see galaxies billions of light years away, we cannot see clearly through our own galaxy. The dust that gave birth to planets, that made Earth possible, now blocks our view of the cosmos beyond. We see the universe through a partially obscured window, and we must remember that our map is incomplete. There are galaxies we have not counted, structures we have not mapped, regions of our own galaxy we cannot observe directly. Our knowledge is vast but imperfect, limited by the simple fact that we cannot choose our observation point. Let us attempt the impossible, putting Earth's size in perspective relative to the Milky Way. The numbers involved are so extreme that metaphors strain to capture them, but we must try. Earth is approximately 8,000 miles in diameter. The Milky Way is approximately 100,000 light-years in diameter. 1 light-year equals about 5.88 trillion miles. This means the Milky Way is roughly 588 quadrillion miles across. The ratio between these numbers is difficult to grasp. The Milky Way is about 73 billion times wider than Earth. If Earth were 1 inch across, the Milky Way would stretch roughly 1.15 million miles, or about 5 times the distance from Earth to the Moon. But this linear comparison does not capture the true scale difference. Volume makes it worse. If you could fill the Milky Way with Earths, assuming you could pack them perfectly with no wasted space, you would need approximately 10 to the power of 17 Earths. That is 100 quadrillion planets the size of Earth to fill the volume of the Milky Way. Another way to visualize this: if the Milky Way were the size of the continental United States, Earth would be smaller than a single bacterium. If the Milky Way was scaled down to the size of Earth, our entire solar system would be smaller than a dust particle. Or, consider this: if you could shrink the Milky Way down to the size of Earth, then Earth would be about the size of a single atom in that scaled-down model. We are not just tiny compared to the galaxy. We are atomic in scale. And remember, Earth is not even the largest planet in our solar system. Jupiter has more than 1,000 times Earth's volume. The central star has more than 1 million times Earth's volume. Yet even our star is insignificant compared to the Milky Way's total size. The Milky Way contains approximately 400 billion stars. If each of those stars has an average volume similar to our own, and if we ignore all the empty space between stars, the total volume of stellar matter is still only about 1/1,000,000th the volume of the galaxy itself. Galaxies are mostly empty space, with tiny points of matter scattered throughout. This means that if you were flying through the Milky Way at random, the chances of encountering anything solid are essentially zero. You could travel for millions of years at high speed and never come close to a star or planet. Space is not just big, it is almost entirely empty. From the perspective of the Milky Way, Earth is utterly invisible. If aliens on a planet in another part of the galaxy looked in our direction with telescopes, they would not see Earth. They would not see our solar system. They might not even be able to distinguish our star from the countless others around it. We are one speck among hundreds of billions, completely lost in the crowd. Even our entire solar system, out to the orbit of Neptune, is only about 5.5 light-hours across. The Milky Way is 100,000 light-years across. Our solar system occupies roughly 1/200th of 1/1,000,000th of the galaxy's diameter. If we were to somehow mark the boundaries of human influence, the sphere would be even smaller. Radio signals from Earth have been propagating outward for roughly 100 years, meaning the farthest any human-made signal has traveled is about 100 light-years. This sphere of human influence occupies roughly 1/1,000th of 1% of the Milky Way's volume. In all of human history, we have physically traveled only as far as the Moon, about 240,000 miles from Earth. This represents about 1/4 of 1/1,000,000th of 1% of the distance across the Milky Way. We have barely moved at all on cosmic scales. These numbers are not meant to diminish humanity's achievements. They are meant to establish perspective. Every human drama, every war and peace, every love and loss, every triumph and tragedy has occurred on a planet 8,000 miles across, occupying an infinitesimal fraction of a galaxy that is itself just one among 2 trillion. Carl Sagan called Earth a pale blue dot, a description arising from a photograph taken by Voyager 1 from the edge of the solar system. In that image, Earth appears as a single pixel, a tiny point of light suspended in a sunbeam. If we could photograph Earth from the center of the Milky Way, it would not appear at all. We would be too small to register even as a single pixel. This is the scale of our existence relative to the galaxy that contains us. We are infinitesimal, and yet we are here. We exist. We think. We understand these scales. We have measured the galaxy that would not notice if we vanished entirely. There is something profound in this contrast. The smallest of things comprehending the largest of things. A grain of salt understanding the ocean it floats in. The universe is not static. It is expanding, and that expansion is accelerating. This fact, discovered only in recent decades, reveals that the ultimate fate of cosmic structures is dissolution, not collapse. In the 1920s, astronomer Edwin Hubble discovered that distant galaxies are receding from us. The farther a galaxy is, the faster it moves away. This relationship, called Hubble's law, revealed that space itself is expanding, carrying galaxies along with it. For decades, astronomers assumed this expansion would gradually slow down due to gravity. They debated whether there was enough mass in the universe to eventually halt the expansion and cause a big crunch, or whether the expansion would continue forever but gradually decelerate. In the late 1990s, two teams of astronomers studying distant supernovae made a shocking discovery. The expansion is not slowing down, it is speeding up. Galaxies are moving away from each other at an accelerating rate, as if some mysterious force is pushing everything apart. This force was named dark energy, and it is now understood to be the dominant component of the universe. Ordinary matter makes up about 5% of the universe's total energy. Dark matter makes up about 27%. Dark energy makes up the remaining 68%. Dark energy behaves unlike any other form of matter or energy. It does not clump together. It does not dilute as the universe expands. Instead, it remains constant in density even as space expands, meaning the total amount of dark energy in the universe increases over time. And it has a repulsive gravitational effect, pushing things apart rather than pulling them together. The precise nature of dark energy remains one of the biggest mysteries in physics. It might be the energy of empty space itself, a property inherent to the vacuum. It might be a dynamic field that pervades the cosmos. Or it might be evidence that our understanding of gravity breaks down on cosmic scales. We do not yet know. What we do know is its effect. It is tearing the universe apart. On small scales, dark energy is weak. Gravity dominates within galaxies and galaxy groups, holding them together. But on large scales, dark energy wins. Superclusters are not gravitationally bound. They are slowly dissolving as space expands between their member clusters. Laniakea, despite its appearance as a coherent structure, is already fragmenting. The most distant galaxy clusters in Laniakea are receding from each other. Over tens of billions of years, the supercluster will completely dissolve, its components isolated in expanding space. Eventually, even galaxy clusters will begin to fragment. Galaxies on the outskirts of clusters will be pushed away by the expansion, leaving only the densest central regions bound together. Over hundreds of billions of years, clusters will shrink, losing their outlying members to the expansion. But the local group, being relatively small and tightly bound, will survive. The Milky Way and Andromeda will merge as planned, forming a single large galaxy. Triangulum and the dwarf galaxies will likely be absorbed as well, creating one massive elliptical galaxy containing all the matter from our local neighborhood. This merged galaxy will become increasingly isolated. Other galaxies will recede beyond the cosmic horizon, disappearing from view as their light becomes too redshifted to detect. The cosmic microwave background radiation, already faint, will cool and fade into undetectability. Future inhabitants of this merged galaxy will see nothing beyond their own stars. Trillions of years from now, the night sky as seen from the merged galaxy will be almost completely dark. No other galaxies will be visible. No evidence of the larger cosmic web will remain. The inhabitants will look out at empty blackness in all directions. Their own galaxy, an island in an infinite void. The expansion will continue accelerating. More and more distant regions will cross the cosmic horizon. Eventually, even the cosmic microwave background, the afterglow of the Big Bang, will have cooled so much that it becomes undetectable. Future astronomers will have no evidence that a Big Bang ever occurred. On even longer timescales, measured in Google years, 10 to the power of 100 years, even stable structures like galaxies will decay. Stars will exhaust their fuel and fade. Planets will be ejected from their orbits. Black holes will slowly evaporate through Hawking radiation. Eventually, the merged galaxy containing the remains of the local group will dissipate into a thin gas of particles, spreading through expanding space. This is the ultimate fate decreed by dark energy. Isolation, then dissolution, then a cold, dark universe where nothing remains but scattered particles expanding forever into infinite emptiness. No structures, no stars, no life, just darkness and decay. This fate is many trillions of years away, so distant that worrying about it would be absurd, but it is worth understanding. The expansion that never stops will ultimately undo everything gravity has built. Dark energy will win in the end. Our journey through the Milky Way is unimaginably slow by human standards, yet breathtakingly fast in absolute terms. We complete one full orbit around the galactic center approximately every 230 million years. This orbital period is called a galactic year or cosmic year, 230 million years. That timescale is difficult to comprehend. The entire history of human civilization spans only about 10,000 years, less than 1/23,000th of a galactic year. Written language has existed for less than 2% of a galactic year. Modern humans, Homo sapiens, have existed for only about 1,000th of a galactic year. The last time our solar system was in its current position relative to the galactic center, dinosaurs had not yet appeared on Earth. The dominant life forms were the synapsids, early mammal-like reptiles. Pangaea, the supercontinent, was still forming. Earth looked completely different. Since that time, our star has traveled approximately 600 trillion miles through space. We have passed through different regions of the galaxy, encountering different densities of stars and gas, different concentrations of cosmic rays. Each region exerted its own influences on the solar system and on Earth. During the previous orbit before that, approximately 460 million years ago, the first land plants were just beginning to colonize the continents. Before that, 590 million years ago, complex multicellular life was still relatively new on Earth. With the Cambrian explosion having recently populated the oceans with diverse animal forms, our star has completed approximately 20 galactic orbits since it formed 4.5 billion years ago. Each orbit exposed the solar system to the different conditions in different parts of the galaxy. Each passage through a spiral arm subjected us to increased cosmic ray flux as nearby massive stars exploded as supernovae. Some scientists have speculated that these passages might correlate with extinction events on Earth. When the solar system passes through a spiral arm, the increased radiation could affect Earth's atmosphere or trigger climate changes. The theory is controversial, and evidence is mixed, but it raises the intriguing possibility that events in the galaxy shape the evolution of life on Earth. Our speed along this orbit is approximately 514,000 miles per hour relative to the galactic center. At this velocity, we cover about 4.5 billion miles each day. Each year, we travel roughly 1.6 trillion miles around the galaxy. Yet this represents only about 1/10,000th of 1% of the total orbit. The orbit is not perfectly circular. Like planets orbiting the central star, our path around the galaxy is slightly elliptical. We also bob up and down relative to the galactic plane, completing one full vertical oscillation every 60 to 70 million years. Right now, we are very close to the galactic plane, moving slightly upward. Other stars in our vicinity move at different speeds depending on their distance from the galactic center. Stars closer to the center orbit faster. Stars farther out orbit slower. This differential rotation causes the spiral arms to persist. They are not rigid structures but density waves, regions where stars bunch up temporarily before continuing their individual orbits. We are not alone in our journey around the galaxy. The solar system is accompanied by neighboring stars, though those neighbors change over time. Stars have their own random motions superimposed on the galactic rotation, causing them to drift relative to each other. Stars that are close to us now were far away millions of years ago and will be far away again in the future. Approximately 3 million years ago, a star called Schultz's star passed within about 1 light year of the solar system, the closest stellar encounter we know of in recent history. Such close passes are rare but not unheard of. Over the course of a galactic orbit, our star might experience dozens of relatively close encounters with other stars. These encounters are not dangerous unless the passing star comes extremely close, within about 1 light year or less. At such distances, gravitational perturbations could disturb the Oort cloud, the distant shell of comets surrounding the solar system, potentially sending some comets into the inner solar system where they could impact planets. Most of the time, though, our journey is peaceful. We cruise through space at enormous speed, following our orbit around the galactic center, passing through different regions of the galaxy, experiencing different conditions, but rarely encountering anything dramatic enough to significantly affect the solar system. We will complete many more orbits before dark energy becomes dominant on galactic scales. The Milky Way should remain stable for at least another 10 billion years, giving us roughly 40 more galactic orbits before the merger with Andromeda fundamentally alters the structure. After the merger, the concept of galactic orbits will become less meaningful. The new elliptical galaxy will not have organized rotation like a spiral. Stars will move in random orbits, passing through the galactic center in all different directions rather than following orderly circular paths. But for now, we remain on our current path, circling the galaxy every 230 million years. Participants in a cosmic dance that began billions of years ago and will continue for billions more. The observable universe ends at a boundary approximately 46.5 billion light-years away in all directions. Beyond that boundary lies more universe, but it is forever inaccessible to us. Light from those regions has not had time to reach us since the Big Bang, and because of the accelerating expansion, it never will. This creates a profound question. What exists beyond what we can see? The honest answer is that we do not know and cannot know. By definition, regions beyond the observable universe are unobservable. We can theorize, we can extrapolate, but we cannot directly test those theories. The simplest assumption is that the universe beyond the observable region looks similar to what we can see. The same types of galaxies, the same structures, the same physical laws. This is an extension of the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. If this is true, then beyond our observable sphere lie more galaxies, more superclusters, more cosmic web structure, continuing perhaps infinitely. If the universe is infinite, then it contains an infinite number of galaxies. Every possible arrangement of matter exists somewhere. There would be infinite copies of the Milky Way, infinite Earths, infinite versions of you reading these words. This idea, while mathematically possible, is deeply strange to contemplate. Alternatively, the universe might be finite but unbounded, curved back on itself like the surface of a sphere. In such a universe, if you traveled far enough in one direction, you would eventually return to your starting point from the opposite direction. The total universe would be finite in volume, but it would have no edge or boundary. Current measurements suggest the universe is flat or nearly flat, meaning it extends infinitely in all directions, rather than curving back on itself. But uncertainties in the measurements leave room for other possibilities. The true geometry of the universe on the largest scales remains an open question. Another possibility is that our observable universe is just one bubble in a vast multiverse. Inflation theory, which explains the early expansion of the universe, suggests that different regions of space might have stopped inflating at different times, creating separate bubble universes with potentially different physical properties. Our universe would be one bubble among countless others, each forever isolated from the others. In some versions of multiverse theory, these other universes might have different physical constants, different numbers of dimensions, even different fundamental forces. Our universe would be special only in the sense that its properties allow for the existence of galaxies, stars, planets, and life. Other universes with different properties might be sterile, incapable of forming structures complex enough for observers to exist. These ideas venture beyond testable science into speculation. We have no way to observe other universes or regions beyond the observable universe. We must rely on indirect reasoning and theoretical considerations. What we can say with confidence is that the observable universe represents a boundary on our knowledge. We can measure and map everything within it, but we cannot reach beyond. Future observations will not expand this boundary significantly. The accelerating expansion means that galaxies currently near the edge of observability will eventually recede beyond it. In a sense, we are trapped in our observable bubble, able to see only a finite portion of whatever larger reality exists. It is like being a fish in a pond, able to see only as far as the water is clear, with no way to know what lies beyond. This should be humbling. For all our knowledge, for all our measurements of galaxies and cosmic structures, we are fundamentally limited. We see only a fraction of what exists. The true extent of reality might be infinitely larger than what we can observe. Yet, what we can observe is extraordinary. 2 trillion galaxies, structures billions of light years across, a cosmic web spanning the observable universe. This is our view, limited though it may be. Perhaps someday, far in the future, if humanity or our descendants survive long enough, we will develop new ways to probe beyond current limits. Perhaps we will find indirect evidence of what lies beyond the observable universe. Or perhaps we will forever remain confined to our observable bubble, making the best observations we can of the cosmos within reach. Either way, the question remains, what lies beyond? And the answer remains, we do not know. The universe keeps its secrets. We have traveled from Earth to the edge of observable space, exploring structures at every scale. Now we can assemble our complete cosmic address, our position in the hierarchy of everything that exists. Start with the familiar, Earth, a rocky planet 8,000 miles in diameter, orbiting a star of modest size and unremarkable properties. That star, sometimes called Sol, but more precisely just the central star, is one of 400 billion stars in the Milky Way galaxy. It sits 27,000 light-years from the galactic center on the inner edge of the Orion Arm in the galactic disk. The Milky Way is a barred spiral galaxy approximately 100,000 light-years across, containing between 200 billion and 400 billion stars. It is an average-sized galaxy, neither particularly large nor small, rotating once every 230 million years. The Milky Way is one of more than 50 galaxies in the local group, a collection of galaxies spanning approximately 10 million light-years. The local group is dominated by 2 large spirals, the Milky Way and Andromeda, with Andromeda being the larger of the 2. The local group is part of the Virgo cluster, a concentration of more than 1,000 galaxies centered approximately 60 million light-years away. The Virgo cluster is the nearest major galaxy cluster to us and exerts gravitational influence on the local group. The Virgo cluster, along with hundreds of other galaxy groups and clusters, forms the Laniakea supercluster, an enormous structure spanning 520 million light-years and containing approximately 100,000 galaxies. Laniakea is centered on the Great Attractor, a massive concentration of galaxy clusters toward which everything in the supercluster is falling. Laniakea itself is part of the larger cosmic web, a network of filaments and walls surrounding vast voids that extends throughout the observable universe. This web structure represents the largest scale organization of matter in the cosmos. All of this exists within the observable universe, a sphere approximately 93 billion light-years in diameter centered on Earth. The observable universe contains roughly 2 trillion galaxies, each with billions or trillions of stars, organized into the cosmic web structure by gravity acting over billions of years. Beyond the observable universe lies something, more universe, presumably, extending perhaps infinitely, forever beyond our ability to observe or measure. We are confined to our observable bubble, able to see only the portion of reality from which light has had time to reach us. This is our address. This is where we are, Earth, orbiting an average star, in an average galaxy, in a typical group, in a large supercluster, in an observable universe that might be just one small part of something infinitely larger. The scale progression is staggering, from the 8,000-mile diameter of Earth to the 93 billion light-year diameter of the observable universe represents a factor of roughly 10 to the power of 27. Earth is to the observable universe as a single atom is to the entire planet. Yet here we are. On this tiny world, we have measured these vast distances. We have mapped the structure of the cosmos. We understand our place in the hierarchy of scales. From the smallest to the largest, we have comprehended structures that dwarf us beyond any reasonable comparison. This knowledge changes nothing about daily life. You will still wake up tomorrow on the same planet, in the same solar system, facing the same ordinary concerns. The universe's vastness does not make your problems less real or your life less meaningful, but it does provide perspective. Every human drama unfolds on a stage 8,000 miles across, in a galaxy 100,000 light-years wide. In a supercluster, 520 million light-years across. In an observable universe, 93 billion light-years in diameter. We are infinitesimal in scale, yet infinite in comprehension. The Milky Way will not notice when we are gone. Laniakea will not mark our passing. The universe will continue expanding, galaxies receding, dark energy pulling everything apart, completely indifferent to whether we exist or not. But we are here now. We see these structures. We understand these scales. We have traced our position from the smallest grain of rock to the largest filaments of the cosmic web. A species 800,000 generations removed from primitive ancestors has measured the universe and found its place within it. That is remarkable. Not just the measurements themselves, though those are extraordinary, but the fact that we can make them at all. That matter, arranged in particular patterns in human brains, can comprehend the arrangement of matter across billions of light years. This is our true scale, not our size, which is negligible, but our understanding, which encompasses everything from the local to the cosmic. We are the part of the universe that has become aware of itself, measuring its own extent, mapping its own structure, telling its own story. You are a participant in this cosmos, made of atoms forged in ancient stars, living on a world orbiting one of hundreds of billions of stars in a galaxy that is one of trillions. Your atoms will eventually return to the cosmic cycle, perhaps becoming part of future stars or planets, or even future observers who will look up at their night sky and wonder, as you do now, about their place in the immense heaven. This is the true scale of the Milky Way in the universe. Not just numbers and distances, but the profound reality that we are here, aware, measuring, understanding, small in size, vast in comprehension, temporary in existence, eternal in significance. We are here, we exist, we understand, and for now, that is enough.